This is Sung, and I'm the principal and director of Sky Academy. And this episode I'm particularly excited about. Okay, I'm excited about this episode because we've been going through this particular chapter on integration, which I said was the second strand under the umbrella of calculus. And the first strand was differentiation, right? I've kind of introduced integration to you as being the area under a curve, and this particular episode shows you basically how all of that works. It's the methodology behind it, right? And I've labeled or named this episode the fundamental theorem of calculus, and I won't spoil the surprise just yet, but it will come at the end. It has to do with the way that the first strand, differentiation, and the second strand, which is integration, are related to each other, okay? But let's just review what integration is all about. Integration is all about finding the area under a curve. How do we go about doing that? Okay, how do we go about finding the area under a curve? Well, let's have a look. Over here, I actually have a curve. Y is equal to f of x, and it kind of looks like that. And if you notice, what I've done is I've basically, along this curve, divided it up into little strips, right? So you got a strip over here, strip over here, strip over here. What we're trying to do is find the area under the curve from, say, one set point A to another set point B, right? And how do we find the area under that particular curve? Well, there is a methodology behind it, which is really what integration is all about. Each of those strips, right? Let's have a look at each of those strips. Each of those strips can make up two rectangles, or each of those strips can make up a set of rectangles. One rectangle is going to sit slightly below the curve. The other rectangle is going to sit slightly above the curve, right? Let me demonstrate over here. So over here, we have just a slice of that curve. Just say this slice here, right? Just a slice. Now let's call the exact area under the curve A of dx. And the reason why I call it A of dx is the width. Now, dx really just stands for a really thin slice, right? Dx means a really thin slice of width along the x-axis, right? So it's like a, D stands for like delta. You can even write the word, the Greek letter delta x, you might see that. But when it starts getting so thin that calculus gets involved, you use the letter D instead, and it's kind of like a writing algebra D, right? A cursive D, as opposed to the Greek letter D, which stands for a distinguishable but really small increment. Okay, so that's why I've called it A of dx, because it is the area, A for area, of a strip of width dx, which is an increment of x, right? And can you see that area kind of looks like a rectangle up until a point, and then you've got the curve that kind of prevents it from being a rectangle. But you will also notice that to the right of it, what I've done is I've isolated a black rectangle which sits exactly under the area of the curve, the exact area of the curve, and another rectangle with a red tip at the top, which denotes the upper rectangle, the rectangle which is slightly bigger than the exact area of the curve, right? So let's work out the area of one of those strips. Now, in order to work out the area of each of those rectangles, right, basically we're going to use the formula for the area of a rectangle, which is length times breadth, right? Length times breadth. Now, we know that the breadth or the width of the rectangle is dx, a little dx. We just need to work out the height or the length of the smaller rectangle and the height or the length of the bigger rectangle. So the height of the smaller rectangle, do you see, right, is if this is f of x, or sorry, if this is, if this point here has an x coordinate of x, the y coordinate will be f of x. Can you see that? That f of x will be the height of that rectangle, right? But the height of the upper rectangle, the red rectangle, the rectangle with the red tip, will be f of, not x, but f of the next increment along, right? And the next increment along will be x plus the dx. So the next increment along is x plus dx. The y coordinate will be a matter, to find the y coordinate or the height, it's just a matter of substituting that into the function, which is f of x plus d of x. Does that make sense? Good. So basically, what I want you to notice is that the whole area under the curve, let's call that area A, is going to be somewhere in between the sum of upper rectangles and the sum of the lower rectangles. And the sum of the lower rectangles. Does that make sense? All right, cool. So let's come up with an algebraic way of expressing the sum of the upper rectangles. So the sum of the upper rectangles really equal to the sum of f of x plus dx times dx. Do you see that? Height times width, right? Cool. And it's the sum as we move from A to B. So we're going to say as we move from A to B. Does that make sense? Now, the sum of the lower rectangles will be kind of exactly the same, but it will be from A to B for f of x dx. Does that make sense? Because you've got f of x here and d of x there, so it's the sum of all the rectangles that are from f of x to d of x from A to B. Does that make sense? So, what I want you to notice is that the area, and let me just move down here, the area is going to be less than the sum from A to B of f of x plus dx, and the sum from A to B of f of x dx. Does that make sense? All right, let me come around this way because I want to show you something else. Right. As the strips get narrower and narrower, let's say we make d of x approach and equals, well, limit 0, approach 0, right? What that means is that the area of the lower rectangles will get closer and closer to the actual area. It'll get bigger and bigger to the point where it actually approaches the actual area. And by making the strips narrower and narrower, the sum of the upper rectangles will get smaller and smaller until it approaches the actual area. Does that make sense? So what's really going on is that when we apply the limit of d of x approaching 0, what you get is the actual area. So the area is going to be equal to the limit as d of x approaches 0 for the sum of A to B, and let's just use this one for the time being, f of x dx. Does that make sense? That is basically what the area of the curve will be by using this method of integration. Okay, so this is almost like integration by first principles, just as you know, when we did the chapter on differentiation, we did differentiation by first principles. So that is basically how to find the formula for integration. Now, there is a way to write this or to rewrite this in a way that is more in line with calculus notation or integration notation or integral notation, and that is to do this. Another way of writing this is to basically replace the sum with the integral sign, and that just assumes that we are using the sum, all right, or we are finding the sum, and it's from A to B of f of x, which is the function of the curve, which is equal f of x times dx, which is the increment, right? The little tiny strips, the width of the little tiny strips, and we don't need the limit as dx approaches 0 because that is already implied by the integral sign. Does that make sense? So this is basically the integral notation way of basically describing exactly what's going on here. Got it? Cool. All right. So I'm gonna break now because I wanna set up the next part of this video, but I'll see you shortly. Okay? Thank you.